Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and Large Language Models. In the last session we had seen the denoising autoencoder. In this particular session we will see the next regularization technique, which is a sparse autoencoder. So what exactly, from our previous session itself you would have understood that it is mainly used to avoid the overfitting problem. Suppose if you have a data set, in this particular session, in this slide what exactly we are seeing, suppose we have a data set where the number of dimensions of hidden representation is less than the dimension of an input. So when we have an architecture of this nature, so is it not you are forcing the model to compress the input data? Right, the model is forced to compress the input data. Hence, the model is definitely a little attentive when learning the important features. Now, second, what if you have a dimension of an input greater than the size of an or the dimension of an hidden the dimension of an hidden representation? What if it is greater than the input? Suppose if you have something like this. If you have in this way. So what exactly is happening? Is it not there is a very high chance that the model may simply copy the input without learning the meaningful features. So we definitely require a regularized one. So this is what is the introduction we have already seen, and even the diagram also remained the same as our previous one. Here the dimension of an hidden representation is much larger comparing to an input. Now how about this requirement? Even if the dimension is large, still you should the requirement here is, even if the dimension is large, still you should enforce the model to learn the features. There shouldn't be an mapping, simple identical mapping. It should not be identity mapping. It should not be. So even if the hidden representation number of neurons in the hidden layer are more, you should still make the model to learn the important features. How it is possible? Even if there are high, can I make this output as 0, this output as 0, and this as a sparse 0? Can we do this? In that case, what has happened? Number of neurons are now less. So with this, is it not again making sure that it is learning the most important features? Are you getting this concept? Even if the hidden layer has many neurons, our requirement is we still want the model to learn the important features. How? Now we will be applying the sparsity to the hidden activation. What is sparsity here? We'll understand that in a while, but the whole requirement here is we'll be introducing the sparsity to the hidden activation. Now with this, let us see what exactly is the sparse autoencoder. So sparse autoencoder is most hidden neurons. We want the most hidden neurons to stay inactive for most input, or make only few neurons to be active. When there are only few neurons which are active, then we are enforcing it to capture the most important features of the input. So are we getting this? The whole idea here is we have more number of neurons. Because more number of neurons, the problem is overfitting, poor generalization. We don't want that. So we want a regularization technique. What is that regularization technique it is doing here is, even though there are more, keep only few neurons active, most of the neurons should be inactive. So by doing this, is it not we are restricting the model? When there is a restriction, when the neuron is active, it should capture the important features. Now this is what is a sparse autoencoder. If this is the case, we should, the whole concept here is you should add that sparsity. How is that? You will be adding the sparsity by adding a sparsity penalty to the loss function. So far in a plain autoencoder, you just had only the reconstruction loss term. Now to that reconstruction loss term, you are adding one more additional term. That one more additional term is sparse penalty. Now, in this, we know that L reconstruction is how well the input is reconstructed, and L sparsity is penalty when there are too many hidden neurons become active, because we don't want, if the neuron is active, punish it, give the penalty so that it becomes less active. When it becomes less active, the remaining features, remaining neurons will capture the important features. So I think you are getting the overall idea. So we don't want a neuron to be active for most number of times. So it should be remain inactive. So when you make that neuron active, then capture the important features from the data, or important information from the data, from the input. And we have a beta, which is mainly used to control the sparsity, how much sparsity should be introduced. So that beta is a hyperparameter here. So it's a small constant that will be added. So now when I say sparsity, this sparsity can be added in two ways. One, either you can go for KL divergence, or we can go for L1 regularization. So in this particular session, and the original research paper also has applied KL divergence. So we'll be learning that with the KL divergence. Now, what are we understanding? Ultimately, hidden neuron should be restricted, right? If that is the case, so look at the diagram that is mentioned here. Now, I am passing in the data set, I have many number of samples, and there are 4 features. Those 4 features are what is being drawn here, given here. Now, there are 3 hidden neurons. Just for an example, I am giving you 3. It can be any number of neurons. It's okay whether it's undercomplete, overcomplete, any this. For overcomplete, for sure there is an problem. So that doesn't mean that in undercomplete we will not have. So whatever may be the architecture, how do we avoid this problem? Let us look into. So we have an data set which is having 4 features, and there are 4 neurons. Now when I pass the first input, so when I pass the first input, you have a connection like this, you will have a connection in this way, and you will have even connection like this. Let me erase this. So you will have connection to each of this. Then you will have connection to each of this. Right? This is what is a fully connected one. Now, what is a sparse autoencoder is saying? The hidden neuron should remain inactive. That's what it is saying. So which means the focus is more towards this hidden neuron now. So here what exactly is this notation? You can see all of a sudden we are seeing a different notation, because I am trying to retain the same notations as that of the original paper. So here what exactly the notation is? X here is an input X, and 2 indicates at a layer 2, first layer and then the second layer 2, and this J indicates this neuron J, and A indicates the output activation, that is output of that hidden neuron is A. If there is one sample that you are passing, or the first sample or one sample X is given to a network, then the activation of the hidden, this is summation, this is activation. The activation of hidden neuron J is denoted as this. Now, what is this whole term? How is that you will be reading? This A is output of hidden neuron J in a layer 2 for the input X. This is how you will be reading it, right? Okay. So now in general, instead of passing a specific input, I am telling in general ith training sample. How is that you will be writing ith training sample? The ith training sample is denoted in this way. Okay, now let us understand, is this approach is good? That is, for one input, you are making that hidden neuron inactive. For one more input, the hidden neuron inactive. Or can we take up the average of all the samples? For example, what I am trying to say is, when you pass the first sample, here you will get one value. When you pass the second sample, you will get the second value. When you pass the third input, you will get the third value. Fourth sample will get the fourth value here, fifth, and you will get the fifth value. So how many ever training samples you are passing, you will have so many outputs for each of this neuron. Correct? So can we now take the average for all of these? So can you look at this average over the whole training set? So how is that you will take the average? This is for a specific ith one. Average over m samples is add up all of this 1 plus 2 plus 3 plus 4 plus 5, all the values which are coming at that particular neuron. Add up all of this and then take the average 1 divided by m, or whole divided by m. M is number of such samples. What did we do here? So I have just explained you individually each of these terms, but what did we do so far? So if a training samples training a data set is having m samples, here we are going to have m values. Agree? Not only there, here also we will have m values. Here also we will have m values. How m values? When you pass the first sample, is it not the connections are made in this way? So when you pass the second data, when you pass here, the connections are like this. So you will get the second value. Like this, when there are m values, so m samples you pass, m such values we get here. Okay, so take the average of all of those. That's all you understand at this point of time. Now let us understand why we have taken this average. What is the whole intention? So what is a sparse autoencoder? Now within that hidden layer, now this is the hidden layer here. Within this hidden layer, only a small fraction of neurons should be active. So now within this there are 3 neurons. So out of these 3, a small portion of the neurons should be active at a time, or either you consider that, or on average each neuron should be active only rarely. You got the concept? So within the hidden layer, if at all if you have 3, keep only a few neurons active. Either do that way, or because you have considered an average. What is average saying? This is there is one average here, there is one average, there is one average. On an average, each neuron should be active only for some time, or only rarely it should be active. So which means if this neuron is active very rarely, when it is activated, is it not its duty is to capture the important features? This neuron will be very rarely active. When it is active, it has to capture the important information. Are you getting the intuition behind this? So either make a few neurons active, or on an average each neuron should be active very rarely. Okay, so now let us understand this little more mathematically. Now there are 2 things that there is one thing that we have seen. What is that? You have taken an average. By taking an average, that is, what is an average? Average of all the values which are there at the first neuron, you are taking the average of it. You will get one value. That value we call it as rho hat. Okay. Now what is that activation we have got? I mean that value we got, it is an actual average activation. Now if it is an actual average activation, we should have one desired average activation, or a sparsity penalty one. So that we call it as rho. Right. So now we have 2 terms, rho and rho hat. Okay. Rho is desired and rho hat is actual. So what is that sparse penalty or activation sparse autoencoder? What is the sparse autoencoder requirement? The sparse autoencoder requirement is whatever is the average that I have obtained, that should be as close as the desired one. So this is the constraint. The constraint here is the desired activation function should be equivalent to or should be as close as the actual one. Okay, this is the constraint. Now, when it is very close to this value, when both are very close, then give less penalty. When they are very far from each other, then give more penalty. Right. So when now you have just two values. What are those two values? Rho and rho hat. If rho and rho hat values are very close to each other, which means add less penalty. If rho and rho hat are very far from each other, then give more penalty. So far you have understood this. Now, if at all, if you want to know how close they are, how far they are, which means you have to measure the distance between these two. You require some metric to measure. So how much penalty to give, how far they are, how close they are, that is measured using a KL divergence. Right. So what is a KL divergence here? KL divergence is measuring the distance between these two. How much P and rho and rho hat are differing, or how close they are, or how far they are. So KL divergence is used to measure the penalty, how much penalty to give. This is what is the complete formula for KL divergence. So in KL divergence, we have the first term and we have the second term. What is that? We will understand shortly. The if P and if rho and rho hat, if they are very close to each other, which means they are almost equal, then the KL divergence value will be 0. When KL divergence value is 0, which means there is no penalty, or there is a very small penalty that is given, because ideally in a real world never these two will be equal, it will be always approximate very closely. So either there is a small penalty or there is a 0 penalty. When this value and this value are very far from each other, then definitely this value increases. When this value increases, there is a large penalty that is given. So I have still not explained you about this formula. So far what we have seen is our requirement is you have to avoid the overfitting problem. So what is that we are doing? Even if there are more number of neurons at a hidden layer, the requirement here is the neuron should be on an average, every neuron should be active very rarely. If every neuron should, on an average, if every neuron should act rarely, should be active rarely, then you should compare that average with some ground truth average. That ground truth or desired is rho, and the actual average what we have got is rho hat. Now you should compare how far they both are. So for that comparison we require KL divergence. And how is KL divergence formula? This is what is the formula that is given. Now let us understand, it is just not for one neuron. We have all in the hidden layer we have many such neurons. You will be adding up all of those. So how is that you will add? If there are 4 such neurons, it is the KL divergence between the first one, second, third and fourth. You will add up all of those penalties. Now let us understand, this slide is important because you will get the actual intuition here only. So here there are 2 parts. One is active part. The first term in the KL divergence we call it as an active part. Second term we call it as an inactive part. Now what exactly is this active and inactive? What is our requirement? Our requirement is there is a neuron at a hidden layer, and the neuron behavior can be either active or it can be inactive. That's what is our requirement. Most of the time it should be inactive, but sometime it should be active also, which means one particular neuron can act either as can be active or inactive. So its neuron's behavior has 2 sides, active and inactive. Can we compare only how far the neuron, can we check only the active site? That's not correct, right? So we will not fully capture the neuron's behavior if you check only the active side. Therefore, we will be using a KL divergence formula. What is KL divergence formula here? It will be using, one term is an active term, one term is an inactive. We will add up them together so that the total mismatch between these two becomes a penalty. That's what, whether to give more penalty, less penalty. You cannot just consider only one term. You should consider both the terms. This is a theoretical explanation. Let us see this mathematically or with one numerical example. Let us take the, we have rho and we have rho hat. So rho is something which is a desired one. Let us assume that a desired is 0.05. So what is that we are saying? The desired average activation should be 0.05. So here there are two. So desired active part should be 0.05 and desired inactive. So how is that you will be, see, can you see in the formula you have this term and you have this term also. So this rho says active, 1 minus rho says inactive, right? So if rho is 0.05, that is desired active part, then desired inactive part, which is 1 minus rho, is 0.95. Can you able to understand what is that we have calculated? We have just calculated given desired. From this, what is desired inactive we have calculated. Now look at this entire complete problem. Now if this is the desired one, then what is the actual average activation? The actual average activation is, for example, 0.05, which means I am giving a condition where rho is exactly equivalent to rho hat. So rho value is 0.05 and rho hat actual rho is 0.05. Again in this you find out what is actual active and actual inactive. So the actual active is 0.05 and actual inactive, which we are calculating this part, is 1 minus 0.05, which is 0.95. Have you got this concept so far? Now just substitute the values in the KL divergence one. What is the, this is 0.05 and this is also 0.05. That's what is both the terms. Then this value is 0.05 log. Here I have considered log to base 10. So this is 0.05 and this actual is also 0.05. Then 1 minus rho is 0.95. So this is 0.95 and this is 0.95. So can you see this? So since log 1 is 0, so the whole term what we are getting is 0, which means here the rho and the rho hat are same. In our previous slide we have seen, right, when this is the KL divergence term is 0. That's what I am giving one example to you here. So here the KL divergence what we got is 0. Now let us understand what is this active part, inactive part. Now the first term here, the first term what we have, what it is going to check is, it is going to check the correctness of active part. What do you mean by this? The actual one is 0. The actually desired is 0.05 and the actual active is 0.05. Whether that part is it correctly matching? So since here 0.05 and 0.05 they are perfectly matching, there is a perfect match. What this is saying, how often the neuron should be active versus how often the neuron is actually active is what the first part has checked. Second, what is that the second it has checked? This desired inactive is 0.95. and actual inactive is 0.05. That is also matching because there is a perfect match. The total when you add, it is 0. So what is this term saying? This term says how often the neuron should be inactive versus how often the neuron is actually inactive. Did you get this concept? So here KL divergence, it is considering both, that is how often the neuron should be active versus actual active, and how often the neuron should be inactive versus actual inactive. This will give us the overall behavior of a neuron. So that is captured using a KL divergence, which has two terms. The one is checking an active part, second is checking an inactive part. I hope this is clear to you. Now let us get into an sparse autoencoders with the complete numerical example, so that you will understand what is this sparse autoencoders is all about. Let us assume there are 5 samples. When I say 5 samples, what is the meaning of it? There is an data set, and the data set is having 5 features. There are 5 features, and there is a first sample, second sample, third sample, fourth sample and fifth sample. There are 5 such samples. When you pass the first sample, when you pass the first sample to this, is it not you get the value here, 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 you will get the values for all the 7. Do you agree to this? When you pass the first one, you will have the connection, first input, you will have connection to all of this. You will get this value. Say for the same sample, when you will have a connection to all of this. Next, you will have connection to each of this. Then you will have connection to each of this, and then you will be getting. So totally you have obtained the values. So what is that? For the first sample, we have, for the first sample we have these many. Then you will take the second sample. When you pass the second sample, you will get the value here, here. In all these places you will get the value. That value is this. So on, so forth. All the training samples you have passed and you have obtained. So if there are 5 such samples, do you agree you will have 5 such values here? You will have 5 such values. I think you all agree to this. There are 5 such values. Now those 5 such values are each column, correct? These are 5 such values, 5 such values. Do you agree to all of this? Answer is yes. Now, what is that we are, because there are 5 such values, you should take an average of it. How is that you will take an average? This is the formula to take an average. The activation, you will add up all of this and you will divide it with the number of such samples. So you will add and you will divide it with 5 for this particular example. Now what you got? The average of this is 0.0003. It is 0.003. So this is the value that we have obtained. Similar way, you will calculate, this is the average activation of hidden neuron 1. Then you will calculate like this for all other neurons. So for H1, the average activation is this much. For H2, this is the value, all these values. What did we do? Simple. We have taken an M training samples, and then we have passed it to the model. We have obtained M such values for each of the neuron. We have considered we have calculated the average, and the average is shown in this table. Now, what we have obtained is rho hat. There is a desired one. Let us assume that the desired sparse is 0.005. Why is that 0.005? This is just one example. So here the actual average activation is 0.005. Now we have to calculate the KL divergence, how far they are, how close they are. Just by looking at this from human eye, when you look at this, is it not this value is very much close to this value? This is very far, close, close, close. This is very far comparing to this value, and this is very close. So now when can you able to write this? What is that we have calculated? We have calculated a rho hat. This rho hat, you are comparing it with the actual rho. So this value is very close to this value. Okay, this is very, very far. This is very close. Right, very, very close, and this is okay, somewhat it is close only. This is close, this is very far, this is a close. So now the whole concept here is we don't want a hidden neuron to be active for most of the time. The average activation of that particular neuron should be active only rarely. If that is the case, you have to check the average activation. We have done that. You have compared it with the original. We have done that. Now, where the penalty should be more? Definitely the penalty should be given to H2 and H6. H2 and H6 penalty should be given. Why penalty should be given? Because on an average, it is these two neurons which are active for most times. So we don't want, sparse autoencoder doesn't want this. So neuron H2 and H6 are much more active. So therefore, they are firing too often. Sparse autoencoder does not want this. So if it does not want this, it has to give the penalty. How is that it will give the penalty? Now see, this is the table what I have taken it from the previous one. We have an desired sparse which is 0.05, 0.005. Now you have to calculate the penalty. How is that you will calculate the penalty? You have both the values, you have rho and rho hat. So with this, just substitute the values into it, and then when we can calculate what is the KL divergence value. So I am just showing you for one example, and the remaining I am writing it directly. So here rho value is 0.05, 0.005. So that is rho, and 0.003 is rho hat. What is rho hat? It is an average activation of that particular neuron. So just substitute the values. You are going to get this value. So once again, wherever there are numerical values, you can calculate by yourself, and if there are any typos, you can correct it. So here you have got this penalty. Now whatever is this is the penalty. Okay. Now, can you correlate the average value 0.003 is very much closely matching with 0.005, right? So when it is a close match, the penalty should be very minimum, or it should be 0. So here you see there is a very small penalty that you are adding. So similar way, do it for all other values. Second is the actual is 0.005, and then the desired value is 284. So calculate the values, substitute the values into this formula, and then you get this value. Similar way you get this value. So from this table, what are we understanding? Clearly we are understanding that H2 and H6 is the neuron that is average activation. By considering the average activation, we are seeing H2 and H6 is active for most number of times. So we don't want, KL divergence doesn't want that. So if that is the case, more penalty should be given for H2 and H6. When more penalty is given for H2, H6, is it not? It is mathematically proved here. The penalty is high for these two neurons. So when penalty is high for these two, definitely during backpropagation there will be associated weights for these hidden neuron. Those weights will be adjusted. When those weights get adjusted, what is happening? Is it not you are restricting H2 and H6? Now H2 and H6 will not be active for most of the time. So here you are imposing the restriction for hidden neurons. So here clearly the main penalties are coming from H2 and H6, and KL divergence gives larger penalty to H2 and H6. So this is what is the concept. Now on average, neuron is going to be an inactive. What does it mean? It means whenever it is active, then it has to really going to capture most relevant information. This is what is the hidden intuition, right? It is inactive for most of the time, but when it becomes active, it has to capture the information. Is it not some sort of a constraint we have put? It's not very free the way that it was in autoencoder. There is some sort of a restriction we have put, some penalty. Because of the penalty, most of the time it is inactive, but when it comes active, it has to capture. So this is how you are going to impose, you are achieving the regularization. So this is the final slide for sparse autoencoders, where the overall objective here is reconstruction, and for this you are adding the penalty, and that penalty here is the KL divergence one, sparse penalty. Sparse penalty here is KL divergence. Now you see here this particular diagram will give us the entire intuition. You have passed an input. Now in this input, say for example the row is 0.005 and the row hat is 0.003, and this is, let us assume 0.246, and this is 0.004. I am just giving one example to summarize this. Now when you look into this, on an average H2 is something which is active most of the time, but sparse autoencoder says you should not allow it to happen. If it is if it has to restrict this, just imagine if the average activation if it is more, which means this is the neuron which is active. So what sparse autoencoder ensures? Give more penalty. How it gives more penalty? KL divergence. KL divergence automatically increases. Why it increases? When it compares this with this, definitely the value increases. When the value increases, is it not the penalty increases? Now what exactly happens during the backpropagation? Now why penalty increases? This term is definitely high. When this term is added to the loss, definitely the overall loss value is more, the total loss value is more. Now because the loss is more, during backpropagation, when you backpropagate it for H2, are there not these are the values which are weights which are associated with H2? Right. So during a backpropagation, the values which are associated with the neuron that is hyperactive or overactive, what it will do? It will come and adjust the weights. When it adjusts the weights, definitely for the next time H2 will become less active. So when it becomes less active, is it not you have imposed certain restriction for the hidden neuron? So this is all about the sparse autoencoders. During a backpropagation, the network adjusts the weights and bias so that the activation of that neuron decreases. In this way, the overactive neurons are pushed to become less active, and they are less fired neurons. So because the network is not allowed to use most of the hidden neurons freely, it can no longer have that overfitting problem, right? Instead, it is forced to learn you are enforcing that to use only few active neurons, so that when the neurons are active, less number of neurons are active, it is going to capture the important information in the data. So this is what is the sparse autoencoder. So overall, it is you are imposing a certain restriction to the hidden neuron. Hidden neurons. How you are imposing the restriction? Your requirement is, on an average, the neuron should be active rarely. Now, how are you ensuring that if it is active often, you are punishing it? How are you punishing it? KL divergence. You are comparing the average with the desired one. If the values are too different, the KL divergence term increases. When KL divergence term increases, it is being added to this to the loss, right? When this term increases, automatically when it is added something to this, the overall loss increases. When the loss increases, when you are back propagating, you have to update the weights. Now, how are you updating the weights? So definitely these weights, of course, all the weights gets updated, but wherever the neuron, the penalty is more, that particular weights gets adjusted, and its bias also gets adjusted. So with this, you are making neuron less active. So with this, you have introduced some sort of an constraint. When there is a constraint, it cannot just relax by copying the input to an output. It cannot, because you are not allowing it to be active. So when it is active, it has to capture. error. So that constraint leads to an regularization. So with this, we have come to an end of this particular session. In the next session, we will see the last type of regularization, which is a contractive autoencoders. So thank you.